So good afternoon everyone. By the way, my name is Ryan James Ondos and I will be the one to report about the lesson 4 which talks about the spanning sets and linear independence. Okay, so that is our topic for today. So the definition of basis. A set of vectors S is equals to V1, V2, up to Vn. V sub n in a vector space V is a basis for V when the conditions below are true. So makaingon ta nga ang vector space V kay basis siya kung kaning kaning conditions nga naa sa ubos is ma-meet siya. Okay? So number 1 or the first condition is that V spans V sub 2 and S is linearly independent. This definition does not imply that every vector space has a basis consisting of a finite numbers of vectors. This text, however, restricts the discussion to such bases. Moreover, if a vector space V has a basis with finite numbers of vectors, then makaingon ta nga V is finite dimensional. Or otherwise, V is infinite dimensional, which means that the vector space of P of all polynomials is infinite dimensional, as is the vector space C from the negative infinity to positive infinity of all continuous function defined on the real line. So muna siya. And the vector space B is equals to the set of 0 consisting of the 0 vector alone is finite dimensional. So an example. So we have an example here like the standard basis for R cube. Show that the set below is a basis for R cube. Ato siyang i-show nga siya is a basis for R cube. So we have here S is equals to 1, 0, 0, 0, 1, 0, and 0, 0, 1. So solution. In the previous lesson example, it showed that S spans R cube. Furthermore, S is linearly independent because the vector equation C sub 1 1, 0, 0 plus ang C sub 2 which is 0, 1, 0 plus C sub 3 0, 0, 1 is equals to 0, 0, 0 has only the trivial solution. So it means that C sub 1 is equals to C sub 2 is equals to C sub 3 which is also equal to 0. So makaingon ta nga ang S is a basis of R cube. The basis S 1, 0, 0, 0, 1, 0, 0, 0, 1 is the standard basis for R cube. And this can be generalized to n space that is the vectors. An example for a non-standard basis for R cube is that from the previous example, you know that the set S is equals to 1, 2, 3, 0, 1, 2, negative 2, 0, 1, and it does not span R cube. So wala siya nag-span sa R cube. And also, it cannot be expressed as a linear combination of the vector in S. So, example, a non-standard basis for R squared show that the set atong i-show nga ang set S is equals to 1, 1, 1, and negative 1 is a basis for R squared. So the solution is kani siya. According to the definition of a basis of a vector space, you must show, dapat nato ipakita nga ang S nagspan siya sa R squared, and obviously, ang S is linearly independent. To verify that S spans R squared, let X is equals to X sub 1, X sub 2. And kailangan nato mag-represent an arbitrary vector in R squared. That is for us to show that X can be written as a linear combination of V sub 1 and V sub 2. So ato ang i-consider ning equation below. So makita nato nga ang C sub 1 plus C sub 1 V sub 1 plus C sub 2 V sub 2 that is equal to X. So as based atong given, C sub 1 1 1 plus C sub 2 1 negative 1 is equals to X sub 1 X sub 2. So C sub 1 plus C sub 2, C sub 1 minus C sub 2 is equals to still X sub 1 and X sub 2. So what is the next thing that we are going to do? Equating corresponding components yields the system of linear equations below. C sub 1 plus C sub 2 is equals to x sub 1. And also C sub 1 minus C sub 2 is equal to x sub 2. So the coefficient matrix of the system has a non-zero determinant, which means nga ang systems has a unique solution. So S spans R squared. Another example, basis for polynomials. Kailangan natin i-show that the vector space P sub 3 has the basis S is equals to 1, x squared, and x cubed. So, unsaon man nato na? The solution is, it is clear that S spans P sub 3. Nga naman, because the span S consists of all polynomial of the form. So, iha magi-consist ang polynomial of the form sa a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed, a sub 0, a sub 1, a sub 2, and a sub 3 are real numbers, which is precisely the form of all polynomials in P sub 3. To verify the linear independence of S, recall that the zero vector 0 in P sub 3 is the polynomial 0x is equals to 0 for all x. The test for linear independence yields the equation. So makita nato sa ubos nga ang a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 2x squared is equals to 0x, and that is also equal to 0 for all x. This third-degree polynomial is identically equal to 0. From algebra, you know that for a polynomial to be identically equal to 0, all of its coefficients must be 0. So that is a sub 0 is equals to a sub 1 is equals to a sub 2 is equals to a sub 3, and that is equal to 0 as well. So S is clearly linearly independent, and also it is a basis for P sub 3. Example, a basis for M sub 2, 2. So makita nato sa representation below that the set S 1, 0, 0, 0 and 0, 1, 0, 0, bracket 0, 0, 1, 0, and another bracket 0, 0, 0, 1. So the solution, ato ang gamiton ang theorem 4.9, which is the uniqueness of basis representation. So unsa man ang uniqueness of basis representation? That means that if S is equals to V sub 1, V sub 2 up to V sub n is a basis for a vector space V, then every vector in V can be written in one and only one way as a linear combination of a vector in S. An example is of uniqueness of basis representation is that maglet u ta, ilet u ang u sub 1, u sub 2, u sub 3 by any vector in R cube. So, kailangan nato i-show that u is equals to c sub 1, v sub 1 plus c sub 2, v sub 2 plus c sub 3, v sub 3 has a unique solution for the basis S. And that is equal to S is equals to v sub 1, v sub 2, v sub 3, and that is equals to 1, 2, 3, 0, 1, 2, negative 2, 0, and 1. Solution, from the equation u sub 1, u sub 2, u sub 3, makita nato nga ang c sub 1, 1, 2, 3, plus c sub 2, 0, 1, 2, plus c sub 3, negative 2, 0, 1, nag-equate siya into c sub 1 minus 2c sub 3, 2c sub 1 plus c sub 2, 3c sub 1 plus 2c sub 2 plus c sub 3, because ato amanggi add ang duha. So you obtain the system of linear equations below. C sub 1 minus 2c sub 3 is equals to u sub 1. 2c sub 1 plus c sub 2 is equals to u sub 2. 3c sub 1 plus 2c sub 2 plus c sub 3 is equals to u sub 3. So the matrix A is invertible. So you know this system has a unique solution if C is equals to A inverse U. Verify by finding A inverse that C sub 1 is equals to negative U sub 1 plus 4U sub 2 minus 2U sub 3. And atong C sub 2 is equal to 2U sub 1 minus 7U sub 2 plus 4U sub 3. And C sub 3 is equals to negative U sub 1 plus 2U sub 2 minus U sub 3. For example, U is equals to 1, 0, 0 can be represented uniquely as V negative V sub 1 plus 2V sub 2 minus V sub 3. You will now study two important theorems concerning bases, and that will be further elaborated or explained by the next reporter. Thank you.